We are go live.
Great. So we are live. Hello, everyone. This is Siwei from DoraHacks. Thank you all for joining us today for another episode of DoraHacks Space Tech Workshop series. Today, we're really delighted to have Prabhat Phondekar joining us today. Prabhat is doing his PhD in rocket propulsion at Birla Institute of Technology. Today, he will share with us his insights on cryogenic and green propellants. So I'm really excited to hear his insights on this topic, and I'm pretty sure everyone watching who has a passion for rocket science will have some great takeaways. Before we kickstart the session, let me give you a quick introduction about who we are and what we've been working on to foster space tech here at DoraHacks. So for those of you who don't know us quite well enough yet, DoraHacks is a leading global hackathon organizer and developer incentive platform. We love to support innovation in blockchain, quantum computing, space tech, and many more other frontier tech fields. To date, we have supported 8 early stage projects working in the space sector with our ongoing long-term space resources and exploration grant. So everyone building within the space sector is welcome to participate and receive support from us. And more excitingly, last month we launched another actually bigger initiative to foster space tech innovation, which is our Starship Use Cases Hackathon with 100,000 USD in prizes. Considering the vast potential of space exploration offered by Starship's lift capacity, we have developed 18 use cases and 2 open challenges for hackers. Use cases include orbital hotel, space-based farming, routers for global Internet of Things, etc. 2 open challenges are novel satellite constellations and recreation facilities for space hotels. Through this hackathon, we like to motivate all space enthusiasts with engineering skills to build their solutions for space. So feel free to click the links below in the description. There you can find more details about our grant and hackathon programs. The submission portal is open, so feel free to join us now, and we can't wait to review all your submissions and provide support for your projects. Lastly, for the audience during the workshop, please feel free to share any questions you have in the YouTube chat room. I'll make sure to keep an eye on it and make sure to ask Prabhat your questions at the end. Now, without further ado, I'm excited to pass the mic to Prabhat. Welcome. Thanks so much for joining us today. Feel free to kick it off by giving us a brief introduction about yourself before diving into the workshop content.
Okay, thank you so much. Thank you so much, Team DoraHacks. Okay, so I started now. My name is Prabhat Phondekar. Currently, I am working as a PhD scholar in the Birla Institute of Technology in the specialization of the rocket propulsion. I have done my master's in the same institute in the precisely in the rocket propellants. You can say the solid propellants, mainly the green propellant part I'm focusing on, and this is my specialization. I have done my bachelor's from the aeronauticals in the different institute, the Nagpur Institute I'm talking about. Okay, so this is all about my introduction. So I think we have to start our core subject, that is our topic of our today's trending topic of our webinar, that is a cryogenic and the green propellant. Okay, so shall we start?
Yeah, sure. Feel free to
Okay,
share slides.
okay, great. Fine. Just give me some time. I'll start. Yeah, it's processing.
Perfect.
Yes,
It's
yes, yes.
showing up now. Yeah.
Okay, great, great. I hope it is clearly visible to you guys. Okay, great. Fine. So we'll start it from our basic topic, the green propellant. The precise topic name is a green propellant, and why it is known as a green. Okay, it is not looks like a green, and it is not a green color. The green means it will not exhaust any type of toxic gases. I'm talking about, because toxic gases are very harmful to the nature, and this is not an eco-friendly one. So this is a major impact on the nature. Now we have three type of rocket that everyone knows. We have three types of rocket that we are currently using for our big missions. These are the solid rocket, liquid rocket, and the hybrid rocket. Solid rocket means both the fuel and oxidizer are in the same manner in the sense premixed version. Okay, and both the propellant is in the solid format, solid phase. Second one, we have the liquid rockets. Liquid rocket means both the chemicals, means the fuel and oxidizer are in the liquid phase and separately tank stored in the separate tanks. And third one, we have the hybrid rocket. Hybrid rocket is, it is also very great concept, but in the developing stage currently. The hybrid rocket means both the chemicals are in the different phases. Mainly the fuel is in the solid phase and oxidizer is in the gaseous or liquid phases. Okay, so that is known as a conventional or a direct hybrid rocket. So we have these three type of rocket, and in this three type, the liquid propellant rockets are very much used in the today's industry. Very much means it is one of the most efficient type of propellant. Fine. So we'll start with our core topic, the green propellant. So as I have told you, green propellant means it is environment friendly. Green means it is indicating the environment friendly type. So what is the main aim? What is the main motto behind it? To replace the traditional. Now, what is a traditional? Traditional means that we are currently using, that we are using since last century and since so many years that we are using the hydrazine type, even the ammonium perchlorate. Just take an example of ammonium perchlorate. Ammonium perchlorate is one of the most efficient oxidizer till now, and most commonly used, you can say. Okay, but this oxidizer is having a major drawback, and the major drawback is it releases very high amount of toxic gases in the environment. Even you can guess 100 to 250 tons of toxic gases has been released at each launch. I am talking about. Okay, okay, so this amount is a very huge. So now it's time to replace it by our new type of green propellant. So hazardous and environmentally harmful propellant used in the space exploration. So that is our main motto. Traditional propellant, as I have told you, the ammonium perchlorate, that is a part of solid propellant system, and the hydrazine is a part of liquid propulsion system, etc. Exhausted the high amount of toxic chlorine gases. Okay, now the disadvantage. Advantage is it is a green, right? It is a eco-friendly. That is a major advantage. Now disadvantage. Hygroscopicity. Hygroscopicity means the tendency to absorb the moisture. Tendency to absorb the moisture. Tendency to absorb the water content. In the easy language, you can say the water content. Now if any propellant or if any oxidizer is having tendency to absorb the moisture, it means that water content getting increases in the propellant. Now if the water content getting increases, obviously the burning properties of the propellant is getting decreases. Okay, it's getting reduced. So hygroscopicity is a major disadvantage. Second one, the complexity and the cost. Some type of propellant, means some green propellants are having very complex means just give example of cryogenic. Okay, cryogenic is currently we are very much using for our big missions, but it is having very complex design, very complex design. Next, limited availability. For example, HN, the hydroxyl ammonium nitrate, HNF, this type of propellants we are currently using for our solid part, but the availability is very limited. You have to spin, or you have to do so many things, synthesize process, even the filtration, so many processes for this case, and then only you will get that propellant part in the very very less manner. Okay. Then reduce performance. Reduce performance means, as I have told you, the part of hygroscopicity. Okay. So I'll give you one example: ammonium nitrate, then hydroxyl ammonium nitrate. So this type of propellant having the tendency of hygroscopicity. So this um, enhance, not enhance, it absorb the moisture at a very high level. So if any propellant is having high moisture content or high water content, so obviously the performance getting reduced. Storage and handling challenge. Storage and handling challenge, why? Because the this hygroscopicity part. So you have to keep that propellant at a very safe level, or you can say at a very temperature and pressure conditions. You have to check the temperature and pressure conditions in that manner. And even for the cryogenic, we have to take care of each and everything, because cryogenic temperature is a very very low, minus 183 degrees Celsius, minus 253 degrees Celsius. So you can imagine, guys, this temperature is a very very low. So you have to maintain that temperature, otherwise it will convert into the gaseous, or then it will convert, or otherwise it will convert into the solid part. It will get freeze if you are not able to maintain the temperature. Okay, now these are the methods we are using to reduce the harmful gases in the case of solid propellant. These methods are only for the solid propellant. First, non-chlorine oxidizer. Non-chlorine oxidizer means such as ammonium nitrate. The like a very very good example is ammonium nitrate, then hydroxyl ammonium nitrate, then potassium nitrate, sodium nitrate. So this type of green oxidizer also we can use. Ammonium perchlorate is having chlorine atom in that molecular structure. Chlorine element. Chlorine means the chemical formula is NH4ClO4. So chlorine is present there. But for example, ammonium nitrate, the chemical formula of NH3 and NH4NH3. So the Cl is not present. So Cl is the main content there, right? Second one, use of scavenging propellant. Now scavenging means use of sodium nitrate. So basically the sodium nitrate will react with the chlorine atom and it will form a sodium chloride. So sodium chloride is not a toxic, that everyone knows. So that is a method of scavenging propellant. And the last one is a use of neutralization method. Neutralization means use of some metal additives such as aluminium, magnesium, boron, the lithium added, etc., etc. So we can use these metals. We can use the some metal means a powdered form. Okay, powdered form metals in the whole propellant compositions. Then overall toxic level, okay, toxicity of this propellant is getting reduces. And one more advantage is the metal is having high heat of combustion. So basically it releases the very high amount of heat during the combustion process. And one more advantage is density. Metal is having high density. So if you're adding the metal in the overall composition, the propellant density is getting increases. So these are some advantages of this metal additive. So we have three type of methods that we can use to reduce the harmful gases in the case of solid propellants. Okay, next one, these are some examples. The non-green propellants such as the ammonium perchlorate, hydrazine, that is a part of the liquid. Then polyvinyl chloride. Polyvinyl chloride is a fuel part. Okay, but yes, it will also releases the high amount of toxic gas. Now we have the green propellants, the ammonium nitrate, then HAN, hydroxyl ammonium nitrate, then HNF, hydrazinium nitroformate, then ADN, ammonium dinitramide, then potassium dinitramide, sodium nitrate, etc., etc. And in the case of fuel, we have fuel binder, we have the HTPB, hydroxyl terminated polybutadiene. HTPB is also we are currently using for our booster stages, HTPB based propellant. Okay, next one, HP means the hydrogen peroxide. Now, hydrogen peroxide means H2O2. That is H2O2 is a monopropellant. Monopropellant means it can act as a both fuel and oxidizer. So both the chemical, both the compound, both the elements are present in their molecular structure. So we can use that hydrogen peroxide for as fuel also and as oxidizer also. Yes, and it is a green. Next one, the liquid oxygen and liquid hydrogen. And this two combination means liquid hydrogen and the oxygen that we are using for our cryogenic. Yes, and yes, it is a green only. Okay, so next is a cryogenic. Cryogenic means the utilization, production of very low temperature compound. Now, very low temperature means minus 150, minus 200, minus 250, like that. Suppose, see, initially, this compound, this elements is is in the gaseous form. Okay, is in the gaseous form, such as oxygen. Just take an example of oxygen or hydrogen or nitrogen. These are acts as a gas. Okay, yes, a gas होते हैं. These are acts as a gas. But if you decrease the temperature of this gaseous compound, then it will act as it will convert into the liquid. Okay, so each and every compound is having their own liquefaction temperature. For example, oxygen. So if you decrease the temperature at minus 183 degrees Celsius, then oxygen, gaseous oxygen will convert into the liquid oxygen. Okay. Now, why we are doing this conversion part? Why we need to convert this gaseous form into the liquid? What is a basic need? First one, convert convert from gaseous state to the liquid state. Okay, if you decrease the temperature, so basically it will convert into the gaseous into the liquid form. Next one, distance of particle getting shorter. Gaseous particles are randomly moving in the environment, right? Gaseous particle, and this gaseous particle are very dispersed in the environment, you can say. So the density is very low. The gaseous particles are randomly moving, density is a very low. So it is very difficult to fix or to keep this gaseous particle in the closed chamber, right? So you require a very long or very huge volume for it. So that is a main thing behind it. But in the case of rocket, we it is not possible to keep very huge tanks, right? It is not possible to keep a very huge tanks. So that is why we are converting that gas into the liquid. So now this gaseous particle will convert into the liquid particle. So density is getting increases. And if the density is getting increases, the volume is getting decreases because it is inversely proportional to the each other, right? Next one, particle getting frozen. Yes, obviously, initially these particles are randomly moving, but now these particles are getting frozen. You can clearly see in the picture also. Next one, the energy for the movement of particle getting decreases. Energy means these are very active. Okay, the gaseous molecules are very active, so they are having very huge energy initially. But if you reduce the temperature, then it will get freeze, and if it will get freeze, then the energy is also getting reduces. Okay, so cryogenic means use of this all these things at a very low temperature. Okay, now the applications, mainly in the food industries to keep food at a very low temperature. Then the preservatives also to preserve that at a very low temperature for long period of time. Then electronics also, in the electronics, electrical, in these industries also we are using the very low temperature gas. Mostly the liquid nitrogen we are using there. Then last one is aerospace. So in the case of aerospace, the cryogenic propulsion system we are currently using. Okay, now the examples. Okay, now the example: hydrogen, methane, and RP1. So, as we have discussed in the early slides, that we are currently using the hydrogen, right? But why only hydrogen? What is the reason behind it? Why we are using the hydrogen? Why we can't use the other gases, right? Such as a methane, also methane is also we can use there. But why only hydrogen? The reason is hydrogen is having very low molecular weight. The H2 atom, the molecular weight is 2, right? And one more thing, the calorific value of hydrogen is a very high. You can clearly see in the picture, 120 to 142 megajoule per kg. It means that hydrogen required very small quantity of oxygen to burn, and when it burn, it releases a very high amount of energy. Okay, very high amount of energy, heat, very high amount of heat. Now, specific impulse is a very important performance parameters of our rocket, right? Specific impulse is inversely proportional to the square root of molecular weight. Okay, so that's why if any compound such as hydrogen is having very low molecular weight. So low molecular weight compound will give you the very high specific impulse. Specific impulse means amount of thrust generated due to the weight flow rate of the propellant. Okay, T divided by weight flow rate. Next one, the methane is also we can use methane gas. So basically you have to convert that methane into the liquid, then we can use it for our cryogenic. Methane is having little low heat value means the calorific value 50 to 55 megajoule per kg, and the molecular weight is C atom 12 and the H4 means the 16, and the specific impulse is reduced because it is having little high molecular weight as compared to the hydrogen. And the last one is rp1 fuel is also we can use, and it is having 43 megajoule per kg, and the molecular weight you can clearly see here 168. So if the molecular weight is increased, the calorific value and this specific impulse value is also decreases at the same time. Okay, great. Now we will move toward our next slide. This slide is a very important, the mechanism behind the cryogenic engine, because the rest of the things are same. Rest of the things means tank, then pipelines, the injectors, etc. So these systems are very same, but the main complex part is the engine. Okay, engine and its mechanism. Now please listen careful, this is very important. We have two diagrams here. First one, so fuel is coming from the fuel tank, right? At the same time, oxidizer is coming from oxidizer tank. Now, amount of oxidizer and amount of fuel is calculated based upon the O by F ratio. O by F ratio means amount of oxidizer divided by amount of fuel. Okay, so it is calculated divided by based upon the O by F ratio. Now fuel is coming from the tank. You can clearly see here this is a fuel, and the same time the oxidizer is also coming from the oxidizer tank. Now to increase the mass flow rate, to increase the pressure, to increase the mass flow rate, we are using the pumps. Okay, mainly we are using the pump is having very like a vast application even in the all other industries, pumps. Now there are so many types of pump. Okay, even based upon the this power supply, right? Based upon the power supply, the daily use, for the daily use we are using that power supply based pumps, right? But this pump is little different. This is a turbo pump. Now what is the difference between it? First, as I have told you about the power supply pumps, this pump required a huge amount of batteries. Okay, huge amount of batteries. Now weight of battery is very large, right? Weight of battery is very large, so you can't keep that weight in your rocket, right? You can't keep that weight in your rocket. So that is why we can't use the battery based pump. Okay, you can't use the battery based propellant because the weight is a very large. Now second option is a turbo pump. Turbo pump is having a turbines in it. Turbo pump is having turbines in it and the impeller. So basically, impeller will take a propellant from the tank and push it towards the combustion chamber. Okay, so to do this thing, the impeller required energy, right? To do this thing, impeller required the energy. Now this energy will will be given by the turbine, will be given by the turbine via small shaft. Okay, now turbine, so turbine is also required some energy to push it towards the impeller. So turbine required a very small amount of energy. Now how to produce this small amount of energy? Because we have the fuel and oxidizer, only two things here. Okay, so see it carefully. Fuel pump this side, the oxidizer pump this side. The middle one is a turbine, and we have this pre-burner. Okay, means the small combustion chamber. So the small combustion chamber is present here. And what is the use of that small combustion chamber? To produce the heat energy, to produce the energy, and this energy will be taken by the turbine. Okay, as I have told you, the turbine is required some energy, so this energy will taken by the turbine to drive the impeller. So that is a basic mechanism behind it. So fuel is coming from this pump, you can clearly see here the impeller, and the one end is going to the pre-burner, and second end will moving towards the rotational part means the winding part of the nozzle, right? And on the other hand, oxidizer, we have the oxidizer also. So oxidizer, because the combustion process we required oxidizer, even if we are producing a small amount of energy, we require a oxygen supply to burn it. So oxidizer is coming from that side, and one end is moving towards the pre-burner, and second one is moving towards the directly towards the combustion chamber. And in the combustion chamber we have the injector system, right? Injector system means initially this propellant is in the liquid or gaseous form, or so this injector is used to inject the propellant inside the combustion chamber, and this is known as the atomization process also. Okay, atomization process. Okay, fine. So the pre-burner generate the heat, right? So this energy will taken by the turbine to drive the this pumps, okay, the turbo pumps. And the second, okay, and the fuel part, you can clearly see here the fuel will rotate or the wind over this nozzle. Now wind over this nozzle, basically the heat of nozzle or the temperature of the nozzle during the process is very high. Temperature will nearly 3000 to 3500 Kelvin. So you can imagine this temperature is a very high temperature. So fuel, basically in this case the fuel will use as a two things. First one, to uh, graph the temperature means to uh, take the temperature from the winding part. Okay, to take the temperature from the winding part. So basically if fuel will take the temperature of this nozzle, so nozzle temperature is getting reduces. Okay, nozzle temperature is getting reduces. Now this fuel will again wind and then move toward the combustion chamber. Okay, and the oxidizer is coming from the mainstream, then it will inject in the pre-burner also at a very small amount, and then it will move towards the second end is injecting in the combustion chamber. So this is the working principle of the cryogenic type of propellants. In the second figure also you can see here. Now in this case we have two pre-burners. Okay, we have two pre-burners, so we can use the small pre-burners, means the one pre-burner also, and the second one we can use the two pre-burners also. See, this is for the big rockets. Just see it carefully. The first pre-burner in the left hand side and the second one is in the right hand side, and then the mechanism is same. The small amount of hydrogen will move towards the pre-burner, and small amount of oxygen is also moved towards the pre-burner for this small combustion process in it, and then it releases the heat, and this heat will taken by the turbine to drive the impeller at the same time. You can clearly see there. Okay, fine. Then next one, this is a picture. Basically, this is a picture I have taken from the software. Now, these colors are indicating you the heat. Okay, heat content, you can say the heat or the temperature content. Now, this red color is indicating the high temperature compounds, high temperature components, high temperature components, and the blue color is indicating the low temperature component. Okay, so in the case of cryogenic, this is a very big challenge to maintain the temperature, because initially the cryogenic temperature of this propellant, means even the hydrogen oxygen, is a very low. So this temperature, initially it is in the tank, right? But this tank is connected to the pipeline and then it will move toward the combustion chamber. So we have a very different types of pipelines also to maintain the temperature. Otherwise what will happen, if suppose, if any small amount of heat will transfer to the tank or transfer to this pipeline, then this liquid will convert into the gases. And if the gases will generate there, it will expand through it, and then you can't imagine, then the explosions are also happening there. Okay, so this is indicating the temperature based diagram. So we need to maintain the temperature of each and every sections. Okay, next one. Now the materials. The materials, which type of material we can use for the cryogenic one, then what are the properties of that material, and based upon the properties we are using that material for the precise component. Okay, first one, the stainless steel. And stainless steel is having two major properties. First one, good strength. Stainless steel is having very high strength. And second one, the corrosion resistant. It will not reacted with the any type of corrosion materials or any type of spilled propellant, because the if you are using the other type of material, then that readily get corroded. Okay, and the components, the combustion chamber, so we can use this stainless steel for our combustion chamber. Then for the nozzle is also we can use, and for the propellant tank is also we can use. Next one, the aluminum and the titanium alloys. So mainly aluminum and titanium alloys, we can use it for the propellant storage tank, is the outer structural part I am talking about, because it is having a very lightweight. It is a very lightweight material and high strength to weight ratio. So strength is high and weight is low. So this material is having high strength to weight ratio. So propellant tank structure, we are using it for the propellant tank structure. Next one, the copper alloys. Copper alloys having a very major property, that is an excellent conductor of heat. Excellent conductor of heat. During the winding portion that we have discussed in that previous slide, mostly we are using the copper. Suppose if you are using the non-conductor, any material which is having the non-conductor heat property, then heat will not transfer through it. Okay, heat will not transfer to the propellant or to the fuel. So that is why we are using the copper alloys mainly. Then regenerative cooling system. Cooling systems also, for that we can use the copper alloy. So basically the heat will transfer to it, and that heat will captured by the fuel or any type of other coolants also. Where the propellants are circulated around the combustion chamber and the nozzle. Okay, as we have discussed in the last slide. So that part mainly we are using the copper alloys. And for the other type of propellant, even for the solid propellant, we are using the insulator layer, sorry, the igniter layers, insulator layer, inhibitor layers, and the liner layer. Okay, in the case of solid propellant, but in this case, in the liquid propellant, we are using the cooling system to cool down the temperature, because temperature is goes around the 3000 to 3500 Kelvin. Next one, the carbon composite. High temperature resistant carbon composites such as graphite. Graphite is having high temperature resistant property, and this property is a very useful for a throat. Okay, the nozzle throat, this property is a very used, because at a nozzle throat, the all the exhaust gases are coming out from the combustion chamber, then it will expand through the nozzle, right? It expands to the CD nozzle. So throat is having very small cross sectional area. Throat is having very small cross sectional area. So in that, the temperature, sometimes temperature is getting increases. So for that case, mainly we are using the carbon carbon composite to resist the heat transfer, to resist the temperature. Next one, the composite material. So lightweight materials, because these composites are very lightweight and the strength is also very high. So mainly for the outer layer, or even, yes, component outer layer, to like protect it, so we are using the composite material there. Okay, very thin layers. Non-critical structural part, because some parts are very critical at the engine part, so these are very critical, very complex things, but for the major parts we are using the composite as a outer structural layers. And the insulation material, so insulation material mainly for the insulating, the insulating things means reduce the heat transfer, right? Reduce the heat transfer. So for that components we are using the insulation material. In the case of solid propellant, mostly we are using the vulcanized rubber. Okay, vulcanized rubber as the insulator. But in this case, we are using the different material, because we can't use the solid part there. Okay, we can't use the solid part there, so we can use this different materials, and the cooling system as well. The cryogenic propellant tank. Yes, the insulation layer is mostly used for the cryogenic propellant tank. Why cryogenic propellant tank? Because you need to maintain the temperature, such as oxygen and the hydrogen, right? So oxygen is having, the liquid oxygen is having nearly minus 183 degrees Celsius, and the liquid hydrogen is having nearly minus 253 degrees Celsius. So you need to maintain the temperature. Okay, you need to maintain the temperature. So to avoid the heat transfer, to reduce the heat transfer, we are using the insulation materials or insulation layers. Okay, in that case. And even in the tank, we have a very different design, that vacuum space is present there. Okay, vacuum space. What is the use of that vacuum space? To decrease the heat transfer level. Okay, so that is a use of it. Okay. Yes, guys. So thank you so much. So here I have almost discussed the mechanism part of the cryogenic, and even the trending topic, that is a green propellant. In the case of solid part, means the solid propellant, we are able to working on it. Even I am also working on the green propellant, as ammonium nitrate based green propellant. That is a major project topic of mine as a PhD thesis. And yes, so that is very difficult. So I'm facing so many problems during this process. But in the case of cryogenic, we are in the cryogenic means, in the case of liquid, we are currently using the cryogenic. So cryogenic is a very big achievement, and specific impulse is also high, and at the same time the toxicity level is zero. Okay, because the hydrogen and oxygen will not release any amount of toxic there, so that everyone knows. And the in the case of hybrid, okay, in the case of hybrid, we can use the paraffin wax. Then I'll give you an example. Paraffin wax is one type of wax. That wax, in your house also, if you burn a candle, at some time a liquid melt layer will form on that surface, right? So at this means the same mechanism is performed in the combustion chamber. If you are using the paraffin wax, a liquid melt layer will form on that surface, and this liquid melt layer will regrade by the oxidizer supply, and then combustion is carried out. So paraffin wax is a very good example to increase the regression rate. Regression rate is a very important property in the case of hybrid propellant. So basically, how much amount of fuel get regrades due to the oxidizer during the combustion chamber. And the burn rate is also very important property in the case of solid propellant, means how much amount of propellant get burns at that given period of time. Okay, so that is a burning rate. So in the case of hybrid, yes, we can achieve the green because that is a very safer system, one of the very safer system. So hybrid we can achieve, in the liquid also we can achieve, but the hypergolic propellant means the fuel and oxidizer, fuels such as any MMH, or oxidizers such as MON, mixed oxides of nitrogen, or white fumic nitric acid, red fumic nitric acid. If you are using this combination, so basically when these two chemicals gets in touch with each other, when they will impinge with each other, then the rigorous and numerous reactions are carried out. And because of these vigorous reactions, the ignition started. And when the ignition started, so you don't need any type of igniters, because this is very important, because in the case of solid, or even in the case of cryogenic, even in the case of hybrid, we are using the different type of igniters, such as a pyrogen igniter, pyrotechnic igniter, the pipe type igniter, the spark igniter. So this type of igniter we are using. But if you are using the hypergolic, you don't need any type of other ignition system. So in that case, injection is itself acts as an igniter process. Okay, that is an impinging one, a different one. So when they will collide with each other, then suddenly the rigorous reactions will take place and the combustion is carried out. But the hydrazine is not a. Okay, so we are also currently working on the hydrazine, and we can replace the hydrazine by the hydrogen peroxide. As I have told you, hydrogen peroxide is acts as a monopropellant, right? You can act like use as a both fuel and oxidizer at the same time. So for that case also we can use the hydrogen peroxide. But hydrogen peroxide is also having one or two drawbacks in it, such as the complexity is very high. Complexity means first you need to concentrate. So during concentration you have to use that equipment, even you have to wear the gloves, the glasses, all these things, because high concentrated hydrogen peroxide is a very critical to use. Okay, so concentration and the storage part, if you are not maintaining the temperature of that storage part, then it will get degrade. Okay, suppose if you reach the 95% of concentricity, then if you're not maintaining the temperature part, then 95 will convert into the 90, 85. So the performance is also getting reduces. So that is a very good example of green propellant, the hydrogen peroxide. So that is why we are currently not using that. The mainly we are using the hydrazine bed. Hydrazine will give you the definitely good performance, but it is having a major drawback, that is a toxic gas. It will release the toxic gases. Okay, so I hope you understood the concept of green propellant and the trending topic, that is a cryogenic. And mainly cryogenic is a very critical part, but the performance is a very good. And only 6 countries have achieved this performance, and they are currently using for, even in the reusable launch vehicle we can use the cryogenic. And this will give you the very high performance at a very high altitude. Okay, so I hope you understood the cryogenic and the green propellant part. Now if you have any questions, yes, don't hesitate to ask me. Okay, thank you so much, DoraHacks, to conduct such webinar for me and to explore more in this case. Okay.
Yeah, awesome. Thank you so much, Prabhat, for this incredibly insightful workshop. So just let me quickly check the chat room. I don't think we receive any live questions, but we do have audience really appreciating such informative session. So thank you so much. But we do have gathered some questions from our community beforehand. So one question, I think you already mentioned some points in the session, but if you can elaborate more, that's going to be really appreciated. So the question is about green propellant. So they're asking, are there any specific types of missions or applications in the aerospace industry where green propellants are particularly advantageous apart from the environmental benefits.
Particular means, see, in the as a booster stage, mainly in the India I'm talking about, as a booster stage we are using the solid propellant, but rest of the stages, means the second stage, third stage, we are currently using the either the hypergolics and the cryogenic one. So during the booster stage, it will release a very high tons of toxic gases, right? To reduce this, so we are trying to reduce this toxicity level. So we can replace that with the green propellant, and it will like be a very very big achievement for us. So I'm trying to focus on that part. Okay, and even for the small thrusters, even for the micro thrusters we can use, as I have told you, the ammonium nitrate, for example, ammonium nitrate, the burning rate is a very low. Okay, the burn initially the burn rate is a very low. So we need to improve it first. And if you will reach the high burn rate and the high performance parameters, then also then only we can use it for a or for a big mission. Even for the missiles also we can use. So all these things in the missiles, in the booster stage, even the small rocket, the SSLV, SLV. So we are currently using the AP based fuels. So to replace the AP with the AN, that is a main motto behind it. In the case of liquid, yes, we can achieve definitely, and we are trying to decrease the level of hydrazine because it is not a green. But yes, in the case of hybrid, that we have already achieved. But the thing is the solid one. Okay, solid is a major part in these big missions, so we are trying to reduce that.
Got it. Thank you so much for elaborating
Okay.
more on that. So
Oh,
last one is my personal question. So I
sure.
assume you must have followed all the updates in the space industry, especially the world has seen what Israel has achieved, like particularly not long ago, the soft landing on the moon. I'm
Hmm.
wondering, as we look into the future of space exploration, what technologies or emerging trends do you find particularly exciting and promising?
Sure, sure, definitely, definitely. Even we are doing the testings on the reusable launch vehicle. I think you have seen in the YouTube videos. So that is also going to be a big achievement if we could achieve that and launch the reusable launch vehicle. So that is also we are trying for it.
Got it. Thank you.
Okay,
Yeah, so I think we also come up close to time here. So once again, thanks so much for joining us today and presenting this great workshop. Really appreciate it. And before we wrap up, I just want to say once again that our Starship Use Cases Hackathon submission portal is already open. We have prepared a prize pool of 100,000 US dollars and thoughtfully designed 18 use cases and 2 open challenges for hackers to tackle. We also have our space resources and exploration grants program in place to support space innovators for the long term. We welcome everyone who has a passion for space to join us and shape the future of space exploration. So if you want to learn more about us and our initiatives, please feel free to click the links below in the description to our grant and hackathon pages. And we do have more space-related live sessions in the pipeline for you. Make sure to follow us on YouTube and Twitter at DoraHacks so you won't miss out on any of the upcoming sessions or any updates about our initiatives. With that being said, just once again, a big thank you to Prabhat for being here with us today, giving this wonderful presentation. Really appreciate your time, and thank you to all the audience who's tuning in today. We will see you soon. Have a good one. Bye
sure,
bye.
sure. Thank you so much for giving me this big opportunity. Okay, thank you so much, Team Dora.
Thank you.
Okay.
Bye.
Okay, bye bye. Bye bye. Okay.